So it's time for the fun part again. I guess it might even be more fun and interesting if we started the beer and wine early. Maybe for next year we could think about that. But okay, so I put up here kind of our title that we were kind of tasked with. So just you already met me, Sheldon Campbell, Yano, Raphael we saw, and Elena Pirapali from USC, right? Okay, so we've been tasked with, the way I understood it was discussing the WIMP paradigm. To what extent is the WIMP paradigm under stress? Is it? And if so, or when would we expect it to be so? And if that's the case, where should we go from there? How do we decide what to do? So going beyond WIMP is kind of a big task, and we've all seen this before, from a particle physics perspective, there's no shortage of ways to categorize new ideas for what dark matter could be. And so it's a bit daunting to try to cover this and as a community, I guess, to pick out what should we pursue, what is worth putting resources into, and how do we justify that to the public, that this is worthwhile doing. And so some of the questions then that are important to us are what are the motivations that should guide us? And I think this was already touched on a little bit this morning. How do we decide what a good dark matter candidate is? What directions should technology R&D be motivated? There are lots of ideas for moving technologies, trying new technologies, and so how wide do we go? Infinitely wide, or should we target more? Same for theory R&D. I think we can see theory R&D has no problem going wide, but at what point do we want to focus on certain paradigms, as we did with the WIMPs? When it's time, to what extent should we transfer from one paradigm to another the resources needed? And these are the things that we have to decide at some point. There are other categorizations. In terms of, we see the mass diagrams, huge mass ranges, different ideas, and again, via whatever interaction cross-section you might be interested in. We've seen various different diagrams of these sorts through the years, continue to use. So lots of ways of categorizing and trying to think of what makes good candidates, and maybe some of these are our favorites. So I think this is a good opportunity right now to share ideas, share the ideas that excite us. It's too broad to just say, okay, go. And so I'm going to try to put up specific chunks at a time. And so if you're a big fan of a particular space here, maybe your chance to say something great about it will come up. So that's the sense. And so I feel like we should start, we want to talk about going away from WIMPs. We should start with where we are now and make sure we're kind of on the same page. I mean, how should WIMPs be defined? I see a lot of different definitions, even from the panel this morning. There was one of the chalkboards that showed WIMPs across, from 1 GeV up to 30 solar masses. And so some would consider a very particular mass bound, and there's no real defined consensus on what WIMPs are. And so if we want to say WIMPs are totally not natural anymore and we should leave them behind, I think that's a particular paradigm that's in mind. And so maybe as a group, we should spend a minute arguing about what we think a WIMP should be defined as. So clearly, weakly interacting, the weak scale is there at some point. But obviously, that's not always the case, right? There's the WIMP-less paradigm, right? Where right, so you can scale the mass and the coupling together, and so you could go to any mass and just scale the coupling accordingly, and you still get a thermal relic, right? That's the case, right? So we don't have to be stuck to a certain mass weak scale. So why do we stick to the weak scale? Feel free. Oh, who's in charge of the microphone? Oh, okay. So the rule is that we'll take a comment from the front, and then someone at the back has to take a comment, and then someone from the front. And if James doesn't have to be carried to the Athenaeum afterwards, we're not doing our jobs.
So I guess for me, the well-motivated WIMP models are those connected to supersymmetry somehow. Oh. Or am I just not? Okay, that's probably better. Yeah, so I'll repeat what I said. To me, the well-motivated WIMP models are those that are somehow connected to supersymmetry and the hierarchy problem in the standard model, and that kind of naturally sets this electroweak scale. So I suppose you can have a WIMP model with a mass that is orders of magnitude away from like TeV scale, but it becomes a lot less well-motivated from a theory point of view.
Right. So the main idea then is we're sticking with thermal relic, right? That's the main thing, and then the WIMP miracle being this ratio takes a particular value. Is there anything else that should define WIMP? Okay. So yeah.
Not exactly on that, but this conversation just makes me think of sort of an older, bigger picture question. So omega total is 1, and omega matter, dark matter, is a number that, well, I guess my question is how is that motivated, and is there any reason why we should expect dark matter to be a single dominant particle? I mean, right, you described one scenario, and there are others like that, where you could have more than one element of some kind that is that could be contributing to the dark matter. And you had a good example this morning about a simple perspective on dark matter is not necessarily the complete and totally right one. And talking about WIMPs is sort of a convenient label, a convenient parameterization that helps us think about experiments. But I guess I'd be interested in the cosmological perspective that drives us to that. I mean, apart from just talking about it being a thermal relic and having certain properties.
Yeah. Sure. So while the microphone's going, to what Roland said, we wanted some new physics at the weak scale for the hierarchy problem, and this seemed to be it. And so having dark matter tied to the new weak physics seemed to be a great idea, and so suggesting 100 GeV seemed to be a good idea, but it doesn't necessarily need to be the case. Yes?
So the way I try to think about it is that even if we are in an extreme case where the dark sector is as complicated as the Standard model, the Standard model is still dominated by pretty much protons and electrons. So it makes kind of sense to actually have at least one benchmark, which would be kind of the equivalent of, I don't know, a dark proton or something, in the roughly the same mass range where that would be kind of like the first thing that we see. But of course, even if we see that, that doesn't mean that it's the end of the story, and it could be a very complicated sector just like the Standard model.
Yeah, and on that point, so the thing about we picked out the weak mass, but then that came along and picked out the weak coupling at the same time, and so then it seemed like a double miracle in that sense that some people have been calling it, where you have both the weak mass and the weak coupling. Go ahead.
So I'll be a bit of a jerk, but with purpose, and I'll say that the best motivation for WIMPs is that, to the best of our knowledge, dark matter exists. But I think so. But the reason why I make the pedantic statement is I think that what Sheldon wants to get at here is that last point where you want the straw man, where we can say, when are we killing this paradigm? And so I think I think what you're leading to is that at what point do we give up on linking our search for dark matter to the naturalness of the electroweak scale?
Great.
So can I chime in as someone who's not a particle physicist, but it's Wednesday at 5 o'clock. There's still no evidence for supersymmetry. Does that inform this at all?
So is supersymmetry done? So So here, I thought of it as an example where someone tells you, here's 10 buckets, you can't see inside of them, and one of them might have a prize. Now, you've looked in the first 9 buckets and didn't find a prize. Are you excited about looking into that 10th bucket? So that, it depends on the prize.
Sure, it's a Nobel Prize.
Yes. So I feel like that's kind of where we're at with supersymmetry.
But I mean, I want to understand, just in terms of getting back to the motivation for the WIMP miracle and the electroweak scale. I mean, if we're starting to worry about supersymmetry, I don't know, if there are those who are starting to worry about supersymmetry, does that mean we should naturally worry about this WIMP picture, which could be just totally unmotivated? I don't know.
So one of the biggest things about the idea of WIMP is what Sheldon said, what W, where weak doesn't mean small, weak means electroweak, interacting with the H or the W or the Z. And that's really important in this context because that gives you a form to the standard model. Alternatively, a lot of what we've been talking about this morning has been along the lines of warm dark matter, self-interacting dark matter.
I'm so mesmerized by what you were saying.
So for example, one of the earlier comments was about, oh yeah, don't you just classify things according to gauge invariance, Lorentz invariance? Yes, but the gauge group that Haibo is talking about is not the gauge group with respect to standard model. These are self-interactions. So for a lot of the types of astrophysical and cosmological probes we're talking about, and what's really exciting, you don't have to talk about the standard model at all. And so this is why I'm kind of being dismissive about is it a WIMP, is it some kind of KK gauge boson, is it blah, 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 blah. Does it talk to standard model or not? Do we have evidence that dark matter has to talk to a standard model? And that's something you can argue, but that's different from dark matter has to exist, and it's also different from does dark matter interact with itself?
I agree. So naturalness was brought up, naturally. And the main question I have here is, there's a lot of the theory community who really care about this, and there are some interesting reasons to consider this. But do we care in the context of this conversation? Should we care? Does anyone feel strongly about that?
I say no.
Any other? Should we poll? Who really cares?
Can you define the question one more time?
Yeah.
Ask the question.
Who really cares and thinks that naturalness is super important for beyond standard model physics? Okay. And who really cares and says it absolutely does not matter? Absolutely, it's very strong. Okay. And who just doesn't really care either way? All right. And lots of abstainers.
A lot of people who just don't think.
Yeah, we're very nervous here. Okay, so.
Can I add a comment? I think, the naturalness problem, it is a problem. But the thing is that the reason why people are getting into so excited about this naturalness, if you go back like 10, 20 years ago, because you're expecting an experiment. You can test your theory, right? Like SSC, after SSC was, for LHC and the LEP. And now, if you look around, I don't think there's a possibility to have a, the super collider is very low. Maybe you can, China probably will build a Higgs factory, but not, I don't think, 100 TeV collider will be on the way now. Then what are you going to do, right? Your career life is only like 30 or 20 years. Are you going to wait for another, 30 or 40 years waiting for this big collider to build it, to test the model? I believe not, right? So that's the reason why, and personally for me, I was trained a high energy physicist. I was puzzled by naturalness problem. But if you think about this, you may not be able to test your theory in the next 30 years. Are you still going to work on the theory, right? Even the WIMP paradigm, right? So it's a nice story, but we don't see WIMPs yet. But what you can do with WIMPs, right? You still build a model with Z prime, you can test with LHC, and that's all fine. But if you are fine, that's fine. But if you are not fine, you want us to do something else, right? It's mainly like a personal taste, I think. So that's the reason why in my last slide I say that, maybe I talk about SIDM. people, you ask him, are you serious? I show you all the fit. But the thing more interesting as a theorist is that you want to work on something which is interesting. Right? So that is a personal take.
So I hear that we may have new motivations, new theoretical motivations, besides naturalness, besides WIMPs. So that's what we're kind of talking about. So are natural WIMPs kind of dead?
Are direct detection experiments many orders of magnitude more sensitive than the weak scales already?
Right, right. So the question is, with respect to direct detection, and maybe some phenomenologists can answer to this, are there models that, given the way naturalness is defined in terms of parameters and renormalization and so on, are there models that are natural where the scale for direct detection is suppressed? What are the mechanisms?
I can't answer that.
Oh, go ahead, though, if people are thinking about it.
I want to go back to James's analogy because of the lack of direct detection, the lack of detecting dark matter through the experiments. So it's not hitting atoms, right? So I feel like it's in big trouble. The same as supersymmetry is in big trouble. Maybe it's still there, but...
And that's because of the W. Again, the W in weak, right? Right. But if we say WIMPs, and we remove that away from the weak scale, now do we still...
Is it interacting via the electroweak sector of the standard model? If it is, then it's in trouble, in my opinion.
So I think all we care about is thermal equilibrium, so it doesn't need to be an interaction through the electroweak sector by what we discussed, right?
But isn't that WIMPless, right?
That's WIMPless, right.
Well, maybe this is what you were just saying with WIMPless. I've seen many variants of this, but one I liked was capital WIMP, capital W WIMP, and lowercase w WIMP. And I think most astrophysicists, when they say WIMP, really mean lowercase w WIMP, which,
I've not seen that in any papers yet.
But no, I think that's a really important distinction. For the capital W WIMP, I mean, there are counterexamples, right? So if you want, there is parameter space, but how tuned do you want to be? So two examples are...
Let's say 10%.
Huh? Oh, well then what's your metric on the volume of, anyway? The two examples, just as benchmarks, are what are called SUSY blind spots. So this is a paper by Josh Ruderman and friends some years ago, where it's within the MSSM, and you play with the tunings of the mixing so that the electroweak interactions cancel out in direct detection. And maybe the simpler counterexample is when you have inelastic dark matter. So you make they're still WIMPs, they're still weakly interacting, but they're a little bit more complicated. And because of the inelasticity, you don't see them in direct detection, which also emphasizes the importance of complementarity.
Right. So I've seen scans of the PMSSM in December that were just scans of the parameter space and measured naturalness, and they found 10% and less in the PMSSM. No discussion of what the mechanisms are, but they must be, like you said, cancellations. And so if that's still natural or not, but I think that's...
So do you want to bring in...
Yes. Yes. We're going to move on to the next topic now.
All right, we'll do that.
Okay.
So WIMP seems safe for now, but it might depend on what you mean by WIMP. I think that's the consensus here. So if we want to go beyond WIMPs, so Jano, you talked about some ideas for going beyond. What are some of the ideas that guide you when you're looking beyond the WIMP paradigm? Yeah, just be real close.
Yeah, I mentioned in the talk. So one thing that I started this pursuing this idea is the observation that the WIMP miracle is actually not sensitive. It's mostly set by the cross section for the annihilation of dark matter instead of the final state. So if the dark matter is directly coupled to the standard model states, and that's at the annihilation cross-section, then we get a very strongly constrained. But you can still have like a thermal dark matter, even a weak scale dark matter, but they, instead of directly coupled to the standard model, the final state of their thermal annihilation is going to some dark sector states. Then in that case, you actually preserve this miracle for predicting the relic abundance, but the phenomenology will be very different. So, and then this scenario naturally motivates the possibility that there may be a thermal bath of the dark matter or other dark particles itself. And in that case, you actually still have sort of WIMP miracle for the relic abundance, but the phenomenology is completely different.
So anything where you're annihilating to the weak sector, but it's still the same scale of annihilation, the same mass, and all that.
Yeah, you can apply all those, but
right.
the final state is different. So you may think it may not be as well motivated as Susie's scenario, but if you think about, for instance, a Reynolds Sandra model, you could have a IR brane where you can have a singlet, standard model singlet, but they naturally still have like a electron weak scale mass. And if you have other particles in the mediator, they can all be located at IR brane, but they are not necessarily following the conventional WIMP paradigm. But their mass scale at the weak scale is still natural.
So this is, I think, an example of just taking the WIMP paradigm and making a little tweak to it, and adding the dark sector, but keeping all the other ingredients the same,
right.
and then considering broadening in that way.
Yeah.
Are those the appropriate ways people think, or are there other ways to tweak?
Well, I also want to mention that recently there's this neutral naturalness studies, like twin Higgs type of models. In that case, you actually have a separate sector, sort of a hidden sector, but with some interaction, slight interaction with standard model, for instance, through the Higgs portal. And in those scenarios, the hierarchy problem is solved by some neutral particles that's in this hidden sector. So from this twin Higgs scenario, people start to propose some new dark matter models where the dark matter is in the hidden sector. They can be asymmetric or it can be this WIMP type, but the interaction is mostly with this hidden sector. So this is another way that you can actually be they are motivated from this naturalness from the particle physics point of view related to the hierarchy problem, but they open up a whole new window for dark matter models.
Great. So this is another example where it's a more extreme dark sector twinning the standard model or parts of it, but it's motivated by the hierarchy problem. Right. It's a partial solution to the little hierarchy problem in this case. So ideas that address the hierarchy problem are highly valued. Is that right? So these are two roads. You could take an extreme road, but it solves a problem, or you could keep what we have and tweak it just a little bit and go down that way as well. Does anyone have comments on those ideas? What would you prefer between those?
Does it make you nervous that these are guided by theoretical ideas and not data?
We need more anomalies.
I take a bit provocative stand on here. What we are doing here, I think, from my opinion, is anyway crazy. We're looking for something that doesn't taste, that doesn't smell, that is justified by what we understand is 5% of our today's universe, if you do it in energy density. And, well, we are not yet even possible to unify our quantum theory with our understanding of space-time as a whole. And somewhere in that bath of highly uncertainty and tries and error for decades we are in. And so a linear approach is always good to go, but it may not be the one that solves things. If you have tried your linear approach for the last 20 years, that this will be the next 20 years to do. So in that sense, I'd say, well, I accept that we're doing is crazy, you know. We want to find answers to these problems, but maybe a bit open-minded and say, okay, maybe from wherever motivation can come, say, I raise it like emergent gravity theories, etc. Things are thought beyond the linear approach. It may succeed, it may not, but I think we have to be open-minded to these kinds of...
So we're already seeing the Pandora's box that we've opened by just proposing a quantum field theory solution to this. There's a huge space of possible solutions that we're finding, and that could be wrong already. Right. So I think rather than start considering the non-quantum field theory solutions, which could be viable, and there are lots of people trying to do that as well, we might make more progress by taking the crazy step of saying, I'm going to believe quantum field theory is true, is going to be the solution, and let's think about what the best directions to look in there would be. Or does that exist? Is that an ill-posed problem?
So I just had a comment related to what Simon was just saying. So there was an article in Scientific American by Kirshner about a few days ago, saying, you know, it was along these lines roughly, that if we are not seeing dark matter, then it's maybe like it's a fool's errand, since we've been trying so hard for decades. And I think that's really mistaken, actually, from a particle physics, from a broadly particle astrophysics viewpoint. We know that there's a relative neutrino background. I mean, pretty well. And we may not be able to detect this thing in our lifetimes in the laboratory. And there's this huge, and everybody's okay with this statement, that there's a weakly interacting dark radiation background that we may never be able to directly detect, although its gravitational influence, both in the CMB and large-scale structure, we detect. So, you know, I just wanted to kind of like just tap on the astronomers a bit to not think that just because it's not detected in the laboratory that it couldn't just be there and it could just be just beyond the sensitivity, but it could be completely not detectable with anything we can conceive of doing, and it could just be a simple weaker than weak interacting thing.
We're not spending a lot of time looking for some people are.
Yeah.
I mean, I would say that if you're successful and you detect dark substructure that's way below the mass where there's any galaxies, you've detected dark matter. You're done. We don't know what it is still, but I mean, we're done. For me anyway, I'm done. Well, I mean, look, it just seems to me that if you find really strong evidence that there's dark substructure at some mass scale where we know there's no galaxies, it's at exactly the right number that you predict in these simulations, say 10 to the 5 solar mass subhalos, 10 to the 5 solar mass field halos, exactly what you predict in lambda CDM. What else could it, that's really strong evidence that you've detected dark matter. That's particle dark matter. It's going to be really hard to come up with some kind of Mondian extension that makes that happen without any baryons, right? Yeah, I feel like, and that's different. Obviously you want to know what the mass of the dark matter particle is, its interaction strength, all that stuff. You won't know all that stuff, unfortunately. But like in terms of knowing whether or not there's dark matter out there, that's incredibly strong evidence that it's some kind of particle type dark matter, in my opinion, right?
I don't know, maybe I missed something, but so does anybody know any model for the CMB that actually fits the data and doesn't have dark matter?
No, but if this were like a modified gravity conference, that wouldn't convince them, right?
I went to a modified gravity workshop, and I couldn't find anybody who could tell me how they could make it work without dark matter.
Right. I'm on your team, obviously, but I would say it's to play. Right, but to play devil's advocate, they would come back and show rotation curve after rotation curve after rotation curve, and say, you cannot come close to predicting these kind of rotation curves with your silly simulations. And we would say, well, yeah, well, that's because we don't understand baryon physics. And they would say, yeah, well, that's because we don't have a general relativistic theory of gravity yet, but we have this. I'm on your team, but I'm just sort of saying I'm playing devil's advocate here.
Next question. Roland said, why we love WIMP so much. It picked up the weak scale, it solved the hierarchy problem, and got the weak mass. It was great. Are there other kind of theories that kind of fit in that framework that we could love as much or more? Please.
Just trying to be positive. I also like axions as a dark matter candidate, and I think what both of these have in common is that even if we never detected dark matter, if we didn't have any reason to believe dark matter exists, we would still have theoretical reasons to think a QCD axion might exist, and then from that we might conclude, hey, actually this might constitute a form of dark matter. And the same goes for like a lighted supersymmetric particle solving the hierarchy problem, but we're moving on from that.
Yeah. Are you looking forward to any technologies that might be able to see the QCD axion in the near future?
I'm no expert on this, but there's this ADMX experiment in Washington State, and I think they're about to have the sensitivity exactly in the right mass range of about 1 to 10 microelectron volt for the axion mass. And so if the QCD axion, at least, is the dark matter, they would have a good shot at detecting it. I don't know what the exact current status is.
Any other axiophiles in the house?
I mean, there's a whole set of proposed experiments,
right? Actually,
use not so much the ADMX type coupling, not so much the axion E.B coupling, but other couplings. I mean, that make use of time-varying neutron dipole moments or any kind of time-varying couplings, so NMR type searches, Casper, and various other experiments that are being proposed. I think that's quite interesting. Right now, also, none of them have the sensitivity to see the QCD axion, but obviously it takes time. And I think that's an interesting... I'm looking forward to seeing results from those.
What do we learn from them?
Well, if we detect the axion, we learn a lot.
We see an axion, we get a mass, we get a...
We get the mass, we get the couplings. I mean, for the axion is really quite constrained. I mean, if you're then discussing other things like axion-like particles, it's a little bit less clear. I mean, there you're really just learning one parameter, but I think in the context of the axion, you can learn a little bit. The QCD axion, you can learn a little bit more.
Is the production of axions understood? Or that depends on the scenario? Do we get substructure with axions? Can they be cold enough?
You mean if the simulations are understood, or you mean if basic...
You mean these ultralight axions, or more these more...
Well, yeah, so if you go light enough, then they're not... Great.
So for the typical action, so like the 10 to the minus 6 or so, I believe that effectively for the cosmological, the large scale structure, it will effectively behave like CDN. So you wouldn't really have like, big effects on like galaxies or like any astrophysically relevant scales, right? But for the 10 to the minus 22, like or any of these ultralight actions, so there's some simulations now that are like trying to get more robust constraints on like galactic scales, but at least for the large scale structures, you basically can reproduce it with this 10 to the minus 22, 10 to the minus 21 sort of. So there are, as I said, like in the previous section, there are some sort of complications there that may arise. But in terms of a large scale structure, I think it's like kind of pretty robust. So one of the things that it's relevant is that at some point you also have this cut in the power spectrum, like the cutoff. So, so as James sort of said, it's potentially like a field where you can start exploring of like how many halos you have, different redshifts, and basically a power spectrum. So, what's that? Yeah, yeah, yeah. So about. Yeah, so like this effective, the
just different formation history.
Yeah, so that's another thing that's worth checking because you'll have different halo growth and all that. So that potentially also change your reionization history at some point, like and also like how many halos in terms of like, how many massive halos you have, different redshifts and so on. Yeah. So that's where this magic, sort of magic number comes from. So like just like Phil said, right? Like there's this, constraints from, or you believe that it's just like roughly like a kiloparsec cores and all this, killing the number of superstructures that you have in Milky Way type galaxies or so on. So that's where these 10 to the minus 22 or so comes from. So like that basically helps do all these sort of problems.
And these could also give the X-ray line as well, right? My understanding. At the KeV scale. So heavier axion. Okay, the Sub-GeV dark matter framework has really taken off. It's kind of been a huge explosion in the past few years of technologies. There have been these anomalies down here that are also pointing down to less than a GeV. I would say that Atlas has improved their triggers in ways to be able to be more sensitive to dark matter in these small scales. And there are new production mechanisms that are very, very well motivated. Does anyone want to comment on Sub-GeV, what they love about it? So I love it so much, I'll spend 1 minute. Just the SIMP idea really came out as a beautiful idea where you have strongly interacting massive particles. So QCD-like interactions, we're talking barn scale interactions. It actually, in QCD, you can get this 5 pion term if you get a sector with stable pions, that's your dark matter. A 5 pion term creates a 3-to-2 interaction in the early universe that is able to reduce the huge amount of GeV particles you have, but they cannibalize each other, 3 becoming 2, and so you get down to the relic density in this way. It's a beautiful mechanism in that sense, and it fits right into the twin Higgs paradigms that Yano was saying, that solves a hierarchy problem, little hierarchy problem, and it's certainly, in this case, you get the strong scale, interaction scale, the strong mass scale, and strong dynamics come along for the right as well. So in this case, it's like a triple miracle. And so it can be very well motivated, something to look out for.
Is that detecting, I mean, for direct detection, are they different class of experiments, same class of experiments?
Again, that will depend on the nature of the dark sector, what the coupling is. So
okay.
If it's a Higgs mediated, do you have a sense? If it's a Higgs mediated twin Higgs sector, does direct detection have sensitivity? Do you know?
Yeah, Higgs mediated, you mean Higgs mediated dark matter?
Right, like a pion dark matter, twin pion.
What mass are you considering?
GeV mass.
GeV, I think that's hard because even for the weak scale Higgs portal dark matter, there's still a window that's open. And then if you go to Sub-GeV, current direct detection, their sensitivity is not there. So
right.
And then if you add a Higgs portal, the interaction is weaker. Then I think the constraint for the GeV case
maybe where these newer technologies come in here then, but I'm not sure on the sectors that they're probing. I have to be honest. Yes.
There are also interesting constraints on that. So these models have a strong interaction cross-section between dark matter and baryons, right? And so at low masses, well below GeV, there are constraints from the CMB, like recent work by Vera Glusevic and others.
Great.
In terms of cross-section, these constraints are way, way weaker than the kind of cross-sections we probe with direct detection. But in that mass range, they're quite interesting. So I wonder how these models are, how they fare against comparison with CMB.
Well, actually, I want to add that from the collider search, the LHC constraint on the light dark matter with Higgs portal interaction is actually can be much stronger than the direct detection.
Right.
So maybe there's stronger constraint from the collider.
So that'll be interesting to research. Anything more to add about primordial black hole dark matter? Raphael gave a very nice discussion.
Only if people have questions.
One question I can ask for you. How do you feel about the, say, dwarf satellite dynamics kind of bounds that people are trying to place, where if you have primordial dark matter, a black hole dark matter, that you get a coherent effect for that imprints in the distribution of the stars in these satellites. Were you aware of these kind of recent works? Yeah. So they made some pretty strong claims that 30 solar masses, 100%, that you would see these imprints if these have been not stirred up too much in recent lifetime. Okay.
But this is different from Tim Brunswick on the ultra-faint works?
Yes, yeah. This is something else now. This was Kushiapis and Loeb recently came out with this paper. Okay. So we kind of talked about non-trivial dark sectors already, unless anyone else, if we're going to open up to a whole bunch of mediators and different ideas, again, that seems like a whole new Pandora's box, like anything is possible, right? And so what directions are motivating us if we want to consider this? So self-interacting dark matter seems to have data that is starting to motivate it in particular mass scales and particular mediator scales. So maybe that's a framework that people are interested in thinking about. Anything else?
Can you make predictions?
Right.
For any and all of these that you discussed, like the broad categories. But going back to David's comment, like what's the data?
Good. Is there a point writing down a model for which there are no observable predictions?
I mean, or I guess the way I was sort of meaning my question was, it seems like historically we make progress when we see anomalies and then build theories to explain those anomalies, as opposed to sort of believing that we should understand how the universe works a priori and then build models. And it seems like the kind of thing that Haibo talked about was, he said, oh, here's this interesting thing, associated with, say, this density cores that we see at this scale, and then we don't see them at that scale. Let's build a model that goes after those data. To me, that's attractive just because you're building something that's actually looking, trying to reproduce the universe you see. I don't know. I don't know if that's what, and then I think what Leonidas is saying is, okay, then given a class of models, let's make some predictions that then you could then test in the future with W1st or Louvois, just to parrot what he said earlier. Or anything.
Maybe we want to make something up that demands a whole new instrument and really push for that new instrument.
Yeah,
Sorry?
If there's the right, yeah.
Sure.
So let me rephrase, because probably we are a similar generation, but so I think that initially there were very, very few data, right? So people, and then especially after Super Kamiokande result came out, there was a burst in developing extensions to the standard models, right? And so the attitude was, okay, let's take this particle physics model and make the prediction to compare with such and such data. In the past 20 years, we have seen a burst of different types of probes, of different type of data, and so on. So now, I think we are much more data-driven, so that it makes sense, and it's actually happening to reason a little bit the other way around and see, okay, so we have this X-ray data, we didn't go after it, but there is this 3.5 keV line. It's seen in several objects. Shall we take it seriously or not? And shall that thing bump up in our judgment of all the possible prospective dark matter particles? or not. So in my view, it's at least the way I operate, has changed in this respect. Rather than testing every individual particle physics model, try to get an approach in which you see what it is more likely according to how many evidences you have, independent evidences in that respect. So I find particularly interesting the discrepancies among various experiments, although the slight discrepancies, because they may point to something new. Although testing then, these discrepancies may be a pain in the neck, because the other possibilities are systematics. But anyway, so according to me, this is how things should proceed, rather than asking ourselves what's the most natural model or the best candidate a priori at this point.
I think that brings us full circle. Why are we driving to search this dark matter? And I think it is data-driven. We were motivated to do so from data, and that's what we're doing. And we're looking for new data to show us the directions. I think, yeah, data-driven is probably the best way to motivate what we're doing.
You have to have some form of idea what you're looking for.
Sometimes we see the unexpected without knowing it was going to be there. But yes, yeah, we need direction.
Yeah, but so I like this idea a lot. It makes me think of the black body curve. So Planck's constant fitting that was data-driven, and it leads you to quantum mechanics in a sense. But also, so I think that's fruitful. It's probably my favorite way. But also, then you think about Einstein. He wasn't driven by the perihelion of Mercury, right? But I mean, how often does that happen?
He was driven by Michelson-Morley and the equivalence principle. Well, no, general relativity, but Michelson-Morley and electromagnetism. Right.
Okay.
For special relativity.
Yes. Okay, I think we've been given the signal that it's time to go have a glass of wine, and let's thank the panel very much. Thank you, Sheldon. And let's thank the organizers and go have some fun. Thanks everybody. Thanks for the